Hello everyone. Today we are going to continue our video on vector subspaces, and today we are going to start from coordinate vector and go further. Okay, let's see this one. So this is going to be the things that we are going to cover in this video. First we will talk about coordinate vector, then isomorphic and equivalence relation, finite and infinite dimensional vector spaces, linear transformation of a set, dimensions of vector subspaces, and coordinate system. If you don't know, I am following a book, which is this textbook, and it was published by Heritage Publishers and distributors. Okay, so uh, let's see and let's start our lecture from coordinate vector. Okay, so what is a coordinate vector? If we suppose that we have a basis for the vector space V given by these set of vectors u1 up to un, then the linear combination of these basis vectors given by x equals c1 u1 plus c2 u2 up to cn un is said to be the linear combination. And if we consider that the tuple of all the constant coefficients of the linear combination to be this, then this tuple is denoted by this notation: x covered with big brackets, and b stands for basis, and called is the coordinate of vector x with respect to the basis b. So it means that we can think of the coordinate of a vector is, if you consider a two-dimensional plane. Let's suppose this plane is actually not the two-dimensional plane but n-dimensional plane. Then we can think of this coordinate of a vector is a point in the space. Okay, is a point in the space which is denoted by not only the two coordinates but n coordinates. Okay, so we can think of the coordinate of a vector as a point in the n-dimensional space which is denoted by these numbers of coordinates. So that's why it is said to be coordinate vector, or more more technically we can say this is a vector, and it is denoted as this, and this is an x vector which consists of these amount of coordinates. So I think this would be a proper geometrical description of this coordinate vector. So again, to see it again, we can think of it as, let's suppose we have u1 to un number of bases for a vector space V. Then the linear combination, and if we consider a linear combination of those vectors to be x, then the coordinate vector of the x is actually the tuple containing all the constant coefficients from c1 to cn. Okay, and if you see geometrically, then it defines a point vector or a point, just a point in the n-dimensional plane, n-dimensional space. Yes, so that would be the geometrical description. So I think I made it clear. Okay, so this is all about coordinate vector. Okay, let's see a theorem associated with coordinate vector to grasp our concept about coordinate vector more firmly. Okay, let's see this theorem. It says that if B is a basis, then the mapping of x vector to its coordinate vector, this is linear. So if you see this theorem, what are the key words here? First one is basis, second one is coordinate vector, and the third one is linear. So we need to know the definitions of these three keywords, that is basis, coordinate vector, and linear. So let's start with the basis. What do you mean by basis? As you have already studied, that basis means these fundamental set of vectors of any vector space V. That means they exist. Let's suppose x and y exist in vector space V. If that's the case, then x and y both spans these set of vectors, right? That means we can write, actually yes, we can write x and y. We can write x and y as a linear combination of these basis vectors with some constant coefficients attached, different constant coefficients attached to both vectors. Okay, if that's the case, then we can write down the coordinate of x and y is this. We can write down the coordinate vectors of x and y is this. It's just the definition of the coordinate vector that says that the coordinate vector just represents the tuple of constant coefficients, right? So these are the constant coefficients. This is the these are the actually these are the coordinate vectors x and y. Now we have to show that the mapping of x and these is linear. That means we have this, and we have to show the mapping in this is linear. That means we have to prove two things. First one is that if we suppose alpha times of okay, so this means that if we consider a linear combination of between x and y is this, then we have to show that this is equal to alpha x b plus beta x b. That is the definition. This is the first definition of the coordinate vector. And the second one is, if we consider k times of alpha of x, or no, k times of x of b, then it is equal to k times of x of b. This is the second definition of linear mapping. So let's try to prove these both things. So for that, what I supposed two scalars. First one is alpha and second one is beta to be any scalars. When I did that, I found a linear combination of x and y vectors, and I can write them in this form. Since alpha times x vector is all of these things, and b and y is all of these things. After that, what I can do is, since u1 arises in both of these places, so what I can do is I can write the coefficients in this format, in the sum of these two different coefficients, but both are constants, so we again get what we can say, okay, a linear combination, but now the constant coefficients has been changed. Now we can say these constant coefficients, if we write them in the tuple, then we can say that these actually form this coordinate vector. These are just the components of the tuple of this coordinate vector, right? Now, after finding this, our goal is to show that this is equal to alpha times xb plus beta times yb, right? To show that this is a linear mapping, we have to show this. For that, from here, we can proceed in the following way. Let me erase it. So, after that, now we can write this thing in this way. What I did is I separated all the ai terms where I goes from 1 to n, and these are all multiplied by alpha. So this is one tuple, plus for the beta there is another tuple. For the bi's there is another tuple. Now from here what I can do is I can take alpha and beta common out of it, and this tuple, if you can see, then these are just the tuple of, or we can say these are just the coordinate vectors of y with respect to beta basis b, and this is coordinate vector of x with respect to the basis b. So we can write this in this form. Now since we had previously shown this, so we can say since this form the linear combination of this, that's why it is a linear mapping. It is a linear mapping. Now another thing that you have to prove is that if we consider, okay, let me erase it. If we consider a constant k, okay, if we consider a constant k times x vector and the basis of this, then this must be equal to k times of this. Now in our book this is not proven, but actually if we really want to show that this is a linear mapping, then we have two constraints for the linear mapping. First one is the previously shown constraint, and second one is the multiplier constraint. And for that it is easy, so you don't have to be panicked about it. So what we can do here is, now k times of x b, what does it mean? It means that let's suppose if we have, uh, how can I write it? Yes, let's suppose, yes, so we have, you can see it, so you can see that definition from here. Now let's see. So what does this mean? It means that if we suppose x is a linear combination of these basis vectors, let's suppose this linear combination, then k times of x means just k multiplies every term of here, right, of this linear combination. Now if you want to write the coordinate vector of this thing, then we would say it is k times of a1, k times of a2 up to k times of an, as I have written here, right? Then since k is a constant, we can take it out from this from this coordinate vector. So if we take k constant and this is remain, now we know that from this relation, this is just the coordinate vector of x with respect to the basis b. Now since we can see that since k was inside in this basis and k is out of this basis now, and both are equal, that means it also follows a linear mapping. That's why by these two constraints, one is addition constraint, one is multiplier constraint, we can say that this mapping is indeed a linear mapping. Okay, let's see another theorem. It says that the mapping of a vector x to its coordinate vector x b is surjective and injective. Okay, so we have to prove that this linear mapping x vector mapping to the coordinate vector is surjective as well as injective. That means it's bijective. The mapping is bijective. We have to prove that. Now to prove that, you need to first know about the definition of injective and surjective vectors. If you have studied linear transformation properly, you should know these two definitions for the injective and surjective function. Injective function means if a function f which maps x to y is injective, then it must be the case that the function of u must be equal to the function of v, where u and v both lies in the vector x. What does that mean? It means that since it's an injective function means one-to-one function. And one-to-one function is the case when if we consider x vector, and in x vector if we consider two other vectors u and v, then these u and v must be same. Okay, to understand this you should know about the definition of injective function first. Actually, this is not the definition of function, injective function. Actually, to be a function, okay, so actually for yes, let's suppose u and v belongs to x, and let's suppose u and v are not equal to each other. These are two different vectors. Then the injective property says that if the domains are not equal, then the function or the ranges must not be equal. That means this f of u is not equals to f of v. Now mathematicians use this property not in the exact original form but by using the contrapositive of it. It means this also implies that if u and v are equal, then the function, okay, the function or the if the domain are equal, then the range must be equal, right? So this is what we are using, the contrapositive of the actual injective definition. So that means here, if we consider this x to belong to some vector space V, and this coordinate vector to belong to some vector space W, then we can say that let's suppose W and Z belongs to this vector space V. If that's the case, and if these two, if we find out the these are the domains, okay, these are the domains, and let's suppose the ranges after applying the function, after mapping, we got this, and let's suppose this ranges are same. So we are considering that the ranges are same. If we consider these and these to be same, then if it is injective function, then it must be the case that the domains must be equal. That means w vector and z vector must be equal, right? So let's see this. If we consider w and z vector to be equal, actually not the w and z vector, but coordinate vectors of w and z to be equal. That means these are uh, you can think of these as the codomain of w and z. If these are equal, that means these and these are equal, and since the basis is same, it must be the case that each of these components of the coordinate vector must be same, and when the components of the vector are same, the linear combination would be same. That means that the domains, the actual vectors, must be same. So since we have already considered the codomain to be same, the domains are also same. And if that's the property, we know from the we know that it follows the property of the injectiveness. So it is an injective function. Okay. Now to prove the surjective, let's see what we do. Okay. Let's see for the surjective case. Now, first, let's try to understand what the definition of the surjective function is. So, if you go directly just to the raw definition of it, you would see this definition. It says that the range of f is equal to y. Now, what does that mean? It means that if we consider a mapping between x and y, and the mapping is done by a function f, and if that's the case, then for each x, there must exist a y. That means if we apply x to a function f of x, then it must give a y, and such that for every x there exists a y. In our case, if you see it, it means that if we have a x which is a vector, then corresponding to that vector, or for the each element of vector x, for each element of vector x, there must exist corresponding value of coordinate vector. That means that for that means for all x's, for every value of coordinate vector x, for all value of x, there must exist coordinate vectors or the corresponding value of coordinate vector. So that means we have x vector as this linear combination, and coordinate vector of x to be this tuple. That means that for each value of it, there exists a corresponding element of the tuple. Okay, and to show that for every x there must exist a value of this. For that, we can say that since it is it lies in the n-dimensional vector space, and it also exists in n-dimensional vector space, it proves that for each x there exists a value of coordinate vector. Okay, so this is it. I know I made a little bit of here and there, and I couldn't explain it as clearly as I wanted to, but if you didn't get it, I am trying to explain the injective case for the last time, and let's see this. Okay, so here it is. So what we are essentially trying to say here is we have two vector space V and W, and let's suppose V vector space contains X and W contains this coordinate vector. And let's suppose we consider that in this vector space V there exist other two vectors W and Z, which are just the linear combinations of the same basis vectors as X. If that's the case, and if we consider that these, now since we are talking about mapping a function, so we can say that this is a domain and this is range, or this is codomain. That means if we can consider that these to be the elements of domain. So we can say that if these domains are equal, then if it is an injective function, it must be the case that range corresponding to these domains must also be equal. So to show that, what we did is we applied the function which is this coordinate vector function, and from this and this function, since these domains are equal, if function has to be equal, then it means the coordinate vector need to be equal, and since coordinate vectors are equal, we can say the range are also equal, so it is injected. Okay, so this is all about this theorem.